So welcome everybody on the fourth and the last day of our workshop and our course related with Julia programming in all areas of mathematics. Today we've got, as usual, two parts. Before the break, we will take care of everything that is related with differential equations, and after that it will be an interesting part about the distributed computing. And I will be switching between the presentation and the code, this day you should be prepared that some of the codes, the part of the code could be more computationally expensive than from the previous days. So sometimes you will have to wait. Simply you will have to wait for the results, depending on the parameters you will provide for the functions. And just to remind you that it should be working, simply you have to wait. Let's start differential equations in Julia. Maybe high level, like overview of applications of differential equations. There is a star in that, so I asked ChatGPT what it thinks about differential equations and how they can be useful in different areas. And I've got two slides just by showing you that absolutely in every area of science and also our ordinary work, they are used. Sometimes you are not aware of it, but they are. So we can see that we've got obviously physics, from classical mechanics, electrodynamics to quantum mechanics, and engineering a lot. So without that, there won't be any airplanes, any buildings, any cars. Biology and medicine, and everything that is related with dynamics in population, like the growth, not only economic growth, but also growth of the population, and physiology. We, especially during the pandemic, there were a lot of models and things that show us how the diseases can spread or what is the drug absorption in the body in time, how it's changing. Economics, this should be obvious because in also macro and microeconomics modeling, supply and demand, everything that is related with the dynamics, there are partial differential equations involved in that. Chemistry, computer science, environmental science, finance. So if you want to invest in cryptocurrency, probably you should, and you want to profit from that, it would be beneficial for you if you know how to solve some kind of equations and to predict what could happen and simulate everything, and just to minimize the risk. Control system, to be designing the whole of thing from the engineering perspective and application of it. Telecommunication with signal processing, but also pattern recognitions in movements. And of course, we are on MIT and pure mathematics. This is something that it is nice because differential equations are studied as a field on their own, and there may be some other applications in the future that could be invented just by participating in this workshop. So you can see how easy it is to solve some, of course, not all of them, but some of the differential equations using Julia. We will use only two packages today. One is differential equations, and the second is plots, because we want to see what are the results. There is one optional thing. It's a library with some examples. We won't be using them, but there is a part of the code that you can uncomment and you can run it, because there are already prepared examples. You don't have to write it from the scratch. You can use it and check how it works. Unfortunately, sometimes there are some problems. So you have to sometimes make some kind of exercises to use this library. It depends on already dependencies in your system. Differential equations, it should be easy and it should be working just like that. And just by reminding you that there are a lot of Julia packages for solving specific problems, you've got the table with exemplary, with sparse matrices, interpolation, everything that is related with polynomials, with finite differences or integration and optimization. And we will be using this for ordinary differential equations only. So from all of the differential equations, we are not able in hour and a half or so to show all of the packages. So we picked only one, and this is differential equation, and it is for ordinary differential equation. So the easiest one. I mean, the easiest one. All the other are more difficult, usually more difficult, but they exist. So if you want to solve others, of course you can do that, but you have to use some other Julia packages. So I think we are ready to start. And this is a brief introduction to differential equations package. So this one package for ordinary differential equations package, but there is a list of the problems that you can solve using this package. So this is not simple ordinary differential equations, but also, for example, discrete equations or stochastic ordinary differential equations, everything with random or algebraic equations. Also, they are implemented, so solutions and algorithms of for those kind of ODEs are also implemented in this package. And much more. I mean, I will show you only, not going through all of them. And you have to remember that each of those lines, like for example, delay differential equations, is the whole class of algorithms. So behind it, there are plenty of different algorithms. And if you want to get the idea how complicated this task of solving differential equations, ordinary differential equations, is, you have to keep in mind that this list must be multiplied by 10 or 20, because in each class of this kind of exemplary differential equations, there are plenty of different algorithms. So there are maybe not thousands, but hundreds of algorithms implemented inside this package, and you can use them depending, of course, on the type of the task you want to solve. One interesting thing that even with partial differential equations, you can solve it using both. Like the classic method is finite differential, finite difference method, but also finite element method is also implemented inside this package. So you can use it as well. And we will skip with the basics, just not to wait. So this is the first one. And the second, just to show you how you can use already implemented algorithms and methods in Julia. What is general approach if you want to solve ordinary differential equations? So there are three major parts of this process. The first one, of course, you have to define a problem. And this definition is not only the function, but we will see that you need more to solve. On the paper, you can, in maybe not many, but in some cases, we know what is the result. We know what is the solution. But in most of the cases, it is impossible to find the exact solution or to write the function. So we are able to solve it only by using the numerical methods. So we are using this package to solve ordinary differential equations using numerical methods. So this is only an approximation. It's not the real solution. It's only an approximation. How good this approximation is? Of course, it depends how good you want it to be. If you want it to be quite exact, you have to spend much more time for the calculations and for solving this problem. And again, to get this as simple as it could be, if you want to calculate the derivatives from the computer point of view, it's easy. So you can implement it, and it's rather easy task. But if you want to reverse the process, so if you want to calculate an integral, in most of the cases we can't do that. So we use numerical methods for that. And the same in here. If you want to solve a special task, special types of the ordinary differential equations, we are able to do that. There are some methods of doing that, but in most of the cases, it is not possible to get. So we know that there is a solution. We know that there must be a result, but even if it exists, we don't have any universal, like general method of doing that, except of the numerical approach. So numerical approach means that you will get the result only in specific points. And depending if it's a 2 or 3 or one-dimensional problem, it will be a whole grid on only a few points on the line. But only in these points we'll know the result. This is the solution. If you want to be more exact, you have to use more points than only 10. You get 1,000 of points, and it will take time to solve it. So the first one is define a problem. The second is to solve the problem, and you have to get a specific algorithm for the specific problem. So not all of the algorithms are working. You have to pick the right one to solve the problem, especially if it's a hard one. And at the end, you want to analyze the output. And by analyzing, I mean you want to, for example, plot it. You want to get the points or to compare it with the exact solution or to use it somewhere else. So analyzing the output is a specific part of this process that is important because it validates as well the solution. And this is general workflow, and I will get some information about each of those in the code in Jupyter Notebook that is provided in GitHub. So let's start with defining a problem. So the first part. We've got some ordinary differential equation, and we know let's assume that we know mathematical specification of this problem. So on a slide you see the whole function and the whole equation. What we need, we need 3 specific things to define a problem. The first one is the definition of the function itself. The second, we need to specify the initial condition. Depending on the initial condition, you will get different results. So if it's an exact solution and we know the formula for the solution, it will be a parameter, but this is just a rare case that we can do that. So usually you will specify the initial condition. It will be a number or a vector depending on the dimension of the task, and using that you should be able to get the solution. And of course, the time. You will need to specify the range from what time to what time you are interested in the solution. If you get this range pretty big, then you will have to use a lot of points. And if you want all the nodes, so with the discretization of these differential equations, and if you use a lot of nodes, then the matrices and the system of linear equations that are depending on those number of points will be big, and if they are big, then we will have to spend a lot of time to get the result. So those are the three things that you need to specify, and let me show you on a simple example at the beginning. On a simple example, how you can do that using this package. So I will switch to this. Let me get it like that. It will be better visible. This is linear ordinary differential equation, and this is a simple one with initial conditions is a half, and the parameter that right now it's like a constant. I will put 1.01, And we know what is the exact solution. So we could compare how good the algorithms and the solvers included in Julia in this package are. And so using this parameter, the specific parameter, let me run this parameter like alpha, and this is the whole thing. So this is the only thing you will need, the basic one, of course, without an extra parameters. So there is a definition of the function, there is a definition of the initial condition, there is a definition or formulation of in what range you are interested in to get the solution. There is a definition of the problem, and there is a solution of the problem. So by this simple code, we cover two of those, defining the problem and solving the problem. So two of those. Let's get some details about it. The definition of the function should be obvious. Just by seeing what is the function, it's simply multiplying the parameter by the function u. So this is an easy. And remember that alpha was defined before. Initial condition and time range between 0 and 1 are also obvious. So this is the definition. How to put it into one object? You should use ODE problem. This is the problem definition, and there are three parameters. You have to provide function, initial condition, and this time span. Doing that, you will define the whole problem that can be solved using simple function solve. So this is the problem definition. This is the problem definition. This is the problem solution. Let's run it. So if you run it, maybe I will show you what is the result by plotting it. So right now I will be plotting this approximation of the solution, and remember that we know the actual solution because it's an easy ordinary differential equation. This actual solution is with this dashed line, and the solid line is approximate solution. So it looks, I mean, in the range of the time from 0 to 1, it looks quite nice. I mean, maybe not exact, yeah, but you've got some errors. How to see what is the solution? To see what is the solution, you can check. Like interested in two things. One is the time, and by doing so, the solution is this is our solution of the problem, and this is the object with time, and time is a vector, and as you can see, there is only a 5-element vector. So the definition of the solution was based on only 5 nodes from 0 to 1, and you've got 5 nodes. This is the time, and this is the solution. Also, of course, a vector of 5 numbers. You can calculate solution in any point you want. For example, if you put the solution at a point that it's not one of those, but any other point you want, then you will get the solution. So you can get the solution. It's the interpolation, of course. It's not the exact solution outside of those nodes, but you can get it. You can see that 5 nodes probably are simply not enough. Yeah. So how to suppose that you want this solution to be more accurate? What to do? So if you want to do, there are some parameters in solving a problem. Well, to tell you the truth, there are a lot of parameters. I won't cover all of them, and I won't be explaining all of them. But let's see few that are mostly interested in you are starting your journey with ordinary differential equation in Julia. So let's see something with lower accuracy. And if you want to get the lower accuracy, I will use the same function solve. Before it was used with default parameters. So right now you've got only the problem and no other parameters. So I use default, but I can change it. And there are two parameters that there should be interpreted as tolerance. This is relative and this is absolute tolerance. I put both simple 0.01. If I solve this and plot the solution, let me, okay. I told you that it could take time to solve. Then you can see that the solution is only 4-element vector. So you need 4 nodes to achieve the accuracy with two digits after decimal point. Now, not 5, 4 is enough, but this is an interpolation. So if you see what is the vector, you can see even that you when to start. Yeah. So maybe I will put something more. Let me show you the time. 0, 1, and you've got 2 more nodes, approximately 0.2 and 0.7. Yeah, and you can see it on the plot. So there are only 4 nodes. 1, 2, somewhere in here, and somewhere in here. And it is lower accuracy than before. Before you've got 5 nodes. 5 nodes. So it will closer to the solution. Still not exact, of course, but closer to the solution than this one. So this is lower accuracy. So let's see if we can do better. I mean, not lower accuracy, let's use higher accuracy. And let's get those parameters with different values. And I will put not 0.01, but e to the 10 to the power of minus 14, for example, both of them. And let's see, with this higher accuracy, you've got different solution, and this different solution right now looks perfectly, at least for a human eye. It's obviously it's not perfect, but it's perfect enough in most of the applications. And if you want to see how big is the vector, how many nodes were used to achieve this kind of accuracy, 33. So by default, you've got 5 in this particular case, of course. If you want the lower accuracy, you can use 4 or 3. But if you use 50 or something, that you are so close to the solution that absolutely no one needs better accuracy than this. And of course, remember that this is smooth solution and an easy task. If you've got more complicated problems, then number of nodes will be, as we can see in a minute, not 50, but sometimes thousands. So, and this is why it needs time to calculate, to compute the solution. So you can get access to any vector, and you can also interpolate the solution easily by getting the solve from it. I talked a little bit about the parameters, and I told you that there are some parameters. And by the way, those solver options, there you've got the link for the documentation. And if you want to see all of them, you can. There is a link to that. I will go briefly through only a few parameters. So what we already know, we know those parameters. This is the relative tolerance, and this is the absolute tolerance. What does it mean, and what are the defaults? The first one, so this is not the same. The first one is rather tolerance on the local error estimates. So it doesn't mean that globally the error is below the threshold you provided. Default is depending on the task. If it's deterministic equation, it's rather 1,000. If it's a stochastic equation, it's 0.01. So 100. This is the relative tolerance, so it could be like on the larger scale, globally, it could be worse than that, but locally, locally, this is the estimate. These are the defaults that are used. You can of course provide it yourself. And absolute tolerance, it is unfortunately still the local one, but those are related. So this is not necessarily global error. In some, depending on the algorithm, but in some algorithms are adaptive. I mean, they are trying, for example, let's try with 5 nodes, and after that it's not enough, so they're calculating an error, it's not enough, and they are using how many nodes? 10, 100, and they can be equally spaced through the time range that you are interested in, but usually in hard cases, there is an adaptive method that you are using more nodes in one area of the solution and not too many in the other. And depending on the algorithm, you can use different parameters. Remember that with stochastic equations, they are a little bit more complicated than the deterministic one. Not to exaggerate. I mean, start with with small parameters just to be sure that you will get the result in reasonable time. Yeah. So those two should be obvious. They are responsible for errors, but you've got more. More than that. One of them is the maximum number of iterations. A maximum number of iterations before stopping, and the default is 10,000. But remember that it depends on the task. So if you've got system of ordinary differential equations and a lot of nodes using it, then probably using this number of iterations will take hours or days. So always put maximum number of iterations because you can also start from the point you are ending. So if you've got some approximation of the solution, you can start from it, but at least you will get some approximation in reasonable time. An algorithm. So you can choose algorithms, and by default, the algorithm is simply nothing. So nothing means that this package automatically chooses the best algorithm for you. So we can leave it. But if you are smarter than a computer, if you are smarter than a library, you've got some other knowledge that will help you to solve this equation, then probably you should use the algorithm that is suitable for these specific problems. I will give you a list of algorithms, or all of them, but a list of algorithms in a moment. Let me go through this through one more parameter. This is a parameter save at, and it denotes specific times that you want the solution at. So you saw that in our case, like let me show you this one. Those are 4 elements and they are not equally spaced, because the method is that, okay, let's use it like closer to the beginning of this interval or closer to the end of the interval. But for the plotting purposes, or if you want to use it farther in specific applications, so maybe you need other nodes surrounded some specific value. So we can provide for the algorithm, you can provide the parameter that will say, okay, I'm interested only in nodes in this, this, and this. And you can provide them exactly in what nodes the solution should be given to you. Okay, so let's go to the algorithm. We are here. I put an extra parameter, and right now I put a simple method because this method could be even computed on a paper. So this is a midpoint algorithm, really easy to implement algorithm, and you can use this because it's already implemented. So I will show you. So you've got the tolerance the same as before, and remember that we've got in this, for those tolerances, both tolerances, and this is the same problem. We've got vector that is consisted of 4 numbers, four observations, 4 nodes. Let's see if changing the algorithm changes something. So the solution looks pretty well, but let me run it and show you how many points. So I run it, and this is the solution, and let's see how many points it is needed using this algorithm to achieve this kind of accuracy. So let's see it. It's 15. So it looks nicer. But to achieve this accuracy with this simple algorithm, you are using 15 nodes, and using different method, you need only 4. Okay? So there are plenty of different algorithms. First, I will show you a list of them. And of course, it's not a full list of those. I provided you with the link. So if you want to see the full list of available algorithms in this package, then, for example, if you need a list of explicit Runge-Kutta methods, then those are the algorithms, and sometimes they are with the parameters. So it's not even one algorithm, but the algorithm with parameter. And in here you've got, of course, Euler method and midpoint enters of the easiest one, and you've got as well more sophisticated methods. And those are the explicit methods. You've got also parallel explicit methods. So the special implementation that is much faster. And it is really important if you are using this for the system of ordinary differential equations, because for the system you want to use the full power of the computer and to speed up the computations. And I will show you on the slides right now how many of them there are. So look at that. So for this, only for this one, I provided you with the list of the algorithms. For all the other, is the same list of algorithms. I mean, not the same, but a lot of algorithms behind the simple line. In each of those, there are several or sometimes a dozen algorithms. So together, this is another slide, so those are the slides. So multi-step methods, exponential propagation, adaptive, non-adaptive, parallel, non-parallel, for stiff problems. All of them, there are also hundreds of algorithms already implemented. Of course, the question is, which one we should use? So my recommendation is, if you are starting your journey with this kind of problems, use the default. Let the Julia to choose for you. But if you see that it's not working, you should use some other algorithms, and you should check what type of problem you want to solve. And there are some like that. Good to go to choices. I mean, if you don't want to go through all of them, this is one slide only that handles pretty good in most of the cases some of the classes of methods. So for example, if you know that you don't know nothing about the equation, you start with something like auto, and there are some other names. But if you know that you want the high accuracy, you should use something else. If this is a standard but non-stiff problem, then this is the first algorithm to try for this one. If you want to be as fast but you are not interested in high accuracy, then, for example, this one. And this is the list of like hints. I mean, there are plenty of others. But if you know that your equations are large or medium size and you want the high accuracy, you don't want the high accuracy, you are rather in the speed, not in accuracy, this is the list, one slide. So you don't have to go through all of the methods. Let's use one of them. So we used the default, we used midpoint, like the simplest one, and let's now use one of those from this slide. Sorry. From this slide, and this is the algorithm. So this is the first algorithm from the list. So suppose I know nothing about the equation, I'm not interested, like, let's start with somewhere. And this is the first from the list. I can put it in here, and I can get the solution with this, of course, with this tolerance, yeah, with this tolerance. And using this tolerance, you can compare like the results, and you can see that those solutions, I mean, let's use this one. So this is the midpoint, 15 element vector, and the one that I used right now is the 4 element. Yeah? So you can see the difference. So the same accuracy with minimum number of nodes. Okay? Minimum number of nodes. This is so of course choosing the right algorithm is important, and you've got the full list of it. But usually at the beginning, just those from the slides that I provided, and it is provided also in the documentation, they are working pretty well. I mean, you can choose one of them, and well, the problem is if none of them is working, then you've got the problem. But of course, you can also implement some your own algorithm. And we've got one more parameter to see how it's working, and this is the save at parameter. So suppose that I add save at 0.4 only, and let's see what is the solution. So the solution is like this, and you can see that it's not smooth. Why it's not smooth? Because it is providing, like in here, the parameter was 0.4. This was the parameter 0.4. So it uses the nodes. It uses the nodes 0, 0.4, 0.8, and of course the end of the interval. So if you want to be more smooth, like nicer, the solution for this one, you should use the smaller parameter save at. If you decrease the value of this parameter from 0.4 to 0.1, to 0.1 in here, you will get the solution that is much nicer. It's not like this, that you've got like 3 lines interpolation, linear interpolation, but it is much nicer. And it is 11 element error because you want it to get the result every 1/10 of, so 0, 0.1, 0.2. If you want more, of course, if you want more, you can do that. So you can use 100 of points. So if you change this parameter into 0.01, and even get rid of, so maybe I will do something like this. If you get rid of all the tolerances and you put the parameter 0.01, then you still, well, it's an easy task, so it should be fast. But you can see that this vector is 101 element vector, yeah, because it's every 0.01. So this is the step it was used to generate this solution. All right, so this should be an easy, quite easy stuff. Let's go through some more examples. The first one is I won't be running it. I want to simply give you the information that there are some predefined problems in a different package, different Julia package. So if you want to use it, this is the code. You have to compile it before, and you can use it. So there is a code if you want to run it yourself. And for this one is an example how to load the specific problem from this library. The next example will be a system of equations. It is especially van der Pol equations. So we know the solution. I mean, and if you want to solve it, it's already in this library, so you don't have to make it. You don't have to define the problem. It's already there. So this is the code if you want to run it using those exemplary files, the exemplary packages and examples from this library. I will provide you my own, implementation, maybe like formulation of this one, because I wanted to show you how to define your own system of equations, this ordinary equations problem. So this is why I'm not using this library with those examples. So this is the case. We've got one parameter mu. We've got there are two equations. So initial point, it's a vector. It's not a number anymore. It's a vector, consists of two numbers. And how to define system of linear equations. This is the implementation of the function with the parameter mu, and you can see that this implementation means that there are two equations, so there are two lines, the first and the second line. In here there are x and y, but I used on like u with 1 and u with 2 instead of x and y. So this is the brief definition, and also those equations are changed. Yeah, so the simpler one is the last one. But as you can see, it's exactly like this. So what is not obvious? Not obvious is the implementation that it's using in-place function. The first function we were using was out-of-place function. It's out-of-place function. There are 3 parameters, and you've got the result. In here, you've got in-place function. And what is the difference? Let me get in here. Oh, this one. This is the in-place function, and this is the definition. So instead of writing a function which gets on output, we can write a function which updates a vector, and it's faster. Unfortunately, you can't do this always, so it's not always the case. So if you want to achieve better performance, and you can do that, you should use in-place function, and it's memory efficient. But if mutations are not allowed, like for the string, yeah. So it's allowed for some numbers, it's allowed for vectors, but it's not allowed for strings. So you can't use it in here. And also there is a convention. It's not must-have. It's not must-have, but it's a convention that if you use in-place function, that the name of the function should end like this. Yeah, it's a convention. So you don't have to do that, but just to give a hint that this function is not returning anything. This is du, and it is the parameter. So out of place function gets 3 parameters, and you get du as a result of the function, output of the function. In place function gets 4 parameters, and one of the parameters is then output. Yeah? So it's memory efficient because it's already reserved, like the memory allocation is already done, and you should simply replace it with the proper numbers. Yeah. So this is why it's faster. Of course, not with so simple examples, but if you've got the big ones, it should be faster. Yeah, it should be faster. So this is the in-place function. So let me run it. And of course, this is only a function. So to define a problem, we should get the initial condition, and we should get the time range. And I use the same as in here. So from 0 to square root of 3, and the time range is from 0 to 1. I will use, so this is the problem definition, and I will use defaults for solving this problem. So to run it, it's not linear problem like this simple one anymore. So we need 54 element vector to achieve the default accuracy. And if you see, this is not in fact a vector. Well, it's a vector of vectors. Why? Because our solution right now, it's not it's two-dimensional problem. So we need both. So we've got the first column and the second column, and they are responsible for x and y, yeah, for those two this is the solution, like two-dimensional solution. And how to plot it, because this is interesting. How to see what is the result? Yeah? We are interested in it. Yeah? We want to see what is the result. And right now we've got two lines. So of course you can get the solution, and automatically it will give you like that. They're both depending on t. So you've got x on one axis and y on the second axis, and in here, like before, we've got t in here and the solution in here. So one of the standard approaches is not to put t, but to plot x and y depending on t on one plot. So we can do that, and this is how it's done. So you've got the indexes 1 and 2, because there are only 1 and 2. Yeah, you've got two-dimensional problem, and you can get a label that one of them is x, the second is y, and they are both depending on t. So this is the equation, and the solution of van der Pol equations. You can do even better than that, because like this, depending on time, but you don't know how it's changing through the time. If it's not one-dimensional problem, like 2 or 3-dimensional problem, you can plot it, and you can animate it. And this is an example of animation. It's already computed. So remember that this animation, especially if there are a lot of nodes, and a lot of nodes means that with this time, it needs to calculate in each time step. This is the solution, and to plot it, it could take time. I mean, if you use plenty of nodes, then you can wait minutes just to generate this animation. So it's fast because it's already been done, and there are some parameters in here. There are more than those, but there are interesting parameters. So one of the parameters is that you can get every second time step. That's plotting it, and if you change it, so I will change it every single one, and let's try to see the animation. And meanwhile, oh yeah, so like that, it's we have to wait. Okay, it's smoother because it's not every second, but it's every single one. And of course, you can also speed up it, like those are frames per second. If you don't want 10, but for example, let's get it 50. So it's 50 frames per second. Then it's much faster, yeah? Much faster. If you put only like 2 frames per second, it will be refreshing every second twice, yeah? So if you put 2 in here, then it's the same animation, but slower, much slower. Like you wait second, you've got one plot, yeah? Like let's wait. Yeah, we have to wait for that. Anyway, oh yeah, it started. Okay, so every 2 seconds, so it's much slower, and it's up to you, of course, if you are interested in something that is fast or slower, and depends on, of course, of the number of nodes in here. And one more, you can give the special file name, and you can simply get it and send to someone. Yeah, it's a simple animation in the file. So you can look that in the folder when you've got the code and this notebook. There should be a file that is generated, and this is the animation. So you can use it even further. Yeah, so you can easily animate the solution of the system of ordinary differential equations. So right now we know, and of course they are both changing in the same time, x and y, and this is a way to show how it changed simultaneously one and the other part of the solution. Yeah. So you can use both, like this plot or animation, to visualize the output and the solution of this ordinary system of equations. let's get, yeah, this is, I've got more examples. We've got one-dimensional problem, we've got two-dimensional problem, so let's get to three-dimensional problem. And let's use the simple one. And the simple one is the system of equations, and there are Lorentz equations, and it's 3D. So I've got x, y, and z in the same. So I will define an in-place function, and this in-place function gets some parameters. So what are the parameters? We've got the parameter sigma, and I put 10 for sigma. There is rho, and I put 28 for rho. And there is beta, and I put 8/3 instead of beta. And this is the definition of the Lorentz function, because it is this is in-place function. Is the definition. I will need some initial conditions. So it's 1, 0, 0, and the time span is from 0 to 100. Problem ODE problem definition is the standard thing, and I will use all defaults. Right now, I won't use different algorithms. Those are the simple tasks. So by default, it will get you will get the solution easily. And you can see that right now, if I'm running it, you will get a vector. But by default, it's a little bit more complicated. So right now, this is elements that it's counted in thousands. It's not 4 nodes, 10 nodes anymore, or 50. It's 1,281. And those are 3 columns, because it's 3D problem. There are 3 equations, so we've got solutions with 3 of them. Okay, so why 3? Because I want to show you how to get visualization of it. And we've got more possibilities with 1D and more possibilities than with 2D problem, with 2 equations. Yeah, so I've got 3 equations. What can I do? So the first thing I can do, I can plot 3D phase space plot. So get the solution, and those are the indexes. I've got three equations, so 3 solutions, 1, 2, and 3. I can put all of them at the same time on the plot. If I do that, I will get the result. So I've got 1, 2, 3. So this is like x, y, z at the same time. All right. What is the problem with 3D plots? With the 3D plots, the problem is that using this with, like, seeing this with different angle, it will allow you to see what is happening. And how to do this? To do this with the 3D plot in here. So I want to see it from the other side, for example, or from above, or from below, or rather from one angle, like, you know, then the other. And this camera. So this is the default. So if you provide it, if you provide for plot known parameters, it will use default, and default is like that. But you can change it. You can change it easily. So how to? I will explain how to change it. There are 2 real numbers, and they are corresponding with azimuth and altitude, like in reality. And I get the plot from Wiki. So there are 2 numbers. So one is this one. So what is an angle? This one this one. So 2 numbers, and you have to think how to rotate the plot and what is interested, like from what angle, from what side you want to see it. I am providing you exemplary rotations. So the extra parameter is a camera, and this is one number. This one number is this one, and that's so I want to get 25 degrees minus, so to the left. I mean, like I should see it, and minus 75 means a little bit down. So if I do that, this is the plot. Yeah. So I rotate it a little bit left and down. But of course you can rotate it in any other direction. I mean, for example, if you got maybe I will use a different one. Yeah, using the plot, because the solution is there. Simply, if you want to get the visualization of it, you want to see it from different angles. So this is not ordinary differential equation. It's from the plot plot package. So if I've got, for example, this with plus with the or with minus, I will use, yeah, it's rotating somewhere. If you want to see a few of those, I provided you with some different angles, like a standard one. So one is standard 45 and 45. The second is I use 0 and 90 degrees, then 90 degrees and 0, and minus 44, minus 45. And I put it in like together. So we can see this is the standard plot, like default. Then you can rotate it and seeing from different angles. So this is only from like from above, or only from the left, or only from the right. Yeah. So using those angles should be easy. Should be easy to see. And of course, it depends on the equation. Yeah. So for this one, probably the default is pretty good. But if you want to see it rotated like the last one, yeah, you can see how it's changing. Yeah. And it's not about solving, it's about the visualization only, yeah? And it is really important. So if you've got 1, 2, or 3 equations, then the visualization is possible. With more equations, it is quite challenging because you have to choose. And how to choose? So what will happen if you've got more than 3 equations? You can get any component you want. So if you use plot, and you've got indexes, and what are the indexes? You've got indexes like 0, 1, 2, or 3. So it's you use time, the x, the y, and z. So we can choose. For example, if I use 0 and 1, it means that I plot x versus t, versus time. If I use 0 versus 0 and 2, it means that I plot y, so the second equation, versus time. And this is the third equation versus time, but I can use, of course, y versus z, or y versus x, or whatever I want. So just by using which indexes I'm interested in, you can plot whatever you want, and this is it. I mean, you can see how it's. Yeah?
Let's make it. I want to interrupt and propose something. Actually, there's regarding the 3D plots, there's Plotly backend.
Yeah.
So I checked this is working actually. Plotly and Plotly like a function, and rather than switch.
Okay, so I will because we've got 2 minutes. So yeah, so I will do this at the end. Yeah. And that you can rotate it. Usually, if you want, like in an article or something, you can't use this animation. You have to provide, yeah. You have to choose the perfect angle to get it for the master thesis or for something, yeah. But for the presentation purpose only, yeah, it should be like this. So I will animate as well. With these three equations, I will animate, and I've got one more thing that is really important with ordinary equations, and then we can try to, yeah, let's make some like, more interesting. But it's not ordinary differentiation; it's only visualization. I mean, yes, so we can use different library as well for visualization purposes. So if you want to animate it, you can see how it's going on with 3. And you can put in the plot as many equations as you want. So if you get full solution, that it's x, y, and z versus t. Or in this case, it's the first component, the second component, and the third component versus time. And time was from 0 to 100. It's from 0 to 100. So let me show you the definition of it. So it's from 0 to 100. If you use every single frame, and it's 3 equations, so every single one, then it will take probably minutes to generate, and it's easy equation. So be careful with this animation because it takes time. You've got, let's see, you've got more than 1,000 of those. So if you want to use every single one, then the output file will be in megabytes. I mean, 100 megabytes or so. So it will be really big, and it will generate a long time. So this is why in here with this animation, I use every 10th, and it's still like every 10th. It still means that there are hundreds, more than 100 of those to plot. Yeah. So you have to be careful with that. All right. So of course you can define right now. You can define any function you want, or a system of equations any you want. And there are more parameters. So if you know something more about the problem, you can provide it to the solver, and it will speed up the computations. But what is right now, what is missing? It's one thing, and I will go through one more time through the Lorentz equation. So right now the parameters are fixed. In here they are inside the function, and at the beginning, like the first example was like the alpha parameter, and it was outside of the. So you can be inside the function, outside the function. It doesn't matter. Well, it matters for plotting or these purposes, but it means that it is fixed. And sometimes it will be, well, if you want to solve not one differential equation, but many of them, depending on the value of the parameter. So it would be quite nice if you can use it to simply use this parameter inside the function. And you can do that. So how to do that? Let me show you. This is defining functions with parameters. I will do this for the first example that was at the beginning. It was the easiest one, so I don't have to wait for the result. And remember, there is an alpha, and this is the parameter. So you can get this with the parameter. Okay, so this is maybe I will explain it like that. It's nothing changed with the initial condition. It's nothing changed with the time span. You've got the parameter, okay? And this was the solution, like with solving, with displaying, with everything. This is exactly the same. But what is the difference? The difference is that this alpha and this alpha can be provided by this parameter. So right now, what is the difference? There is a p in here inside the function, and this is a parameter of the function. It's not the same as in the beginning. Let me show you what was in the beginning. In the beginning, we've got alpha in here, and inside was alpha as well. So there was a parameter p in a function, but it wasn't used. So this alpha was defined outside of the function. But you can use this one, this parameter, inside the function. How it works? Let me go. Yeah, there are a lot of examples, so let me find it. Yeah, this is the one. So right now you are defining alpha, but you are not using this one in here. So this is the function that is depending on the parameter p. And how to solve it? With the solution, with the definition of the problem, there is one extra parameter. So before, ODE problem got only 3 parameters: f, initial condition, and the time span. And this was it. But right now, we've got an extra parameter alpha, and you can provide it with the definition of the problem. So this is constant. I mean, you define it once and for all. And after that, you can define as many problems as you want, depending on the parameter. So for example, this is for parameter alpha, the same as before, and the solution, of course, is exactly the same as before. You've got the solution. Of course, this was an easy task because the parameter was a number, so it was easy to provide a number. But the Lorentz system of the Lorentz equation, so there are 3 equations with this case. And there are more than one parameter, so there are 3 parameters in fact. How you can do this with 3 parameters? Or like more than one, you can get 10 parameters or 2 or 20, it doesn't matter anymore. So instead of a number, you should provide a whole vector of parameters, a whole vector of numbers. And I've got an example. In fact, I've got two examples. So this is the same example with providing different parameter. So you simply change this one, and you don't have to change anything in here. You simply provide a different alpha, and you will get the result. Yeah. So you will get the result. So it's easy thing because it's a parameter. But the last thing I want to show you. Okay, and this is the animation. This is the fast animation. Yeah, you can see it. You can animate as well 1D problems, and depending on alpha, you can see how it's changed. Yeah, so you can get animation, of course, the same with different alphas as well. But what I'm going to show you, it's how to use the parameter when there are more than one number, so more parameters. And in the Lorentz function, we've got the Lorentz equation. There were three parameters. This is one parameter. This is second parameter, and this is third parameter. So we've got three parameters, but the definition of the function is more or less the same. So there is a parameter p, but you have to remember that this is not a number anymore, it's a vector. So if it's a vector, you can get access to every single element of this vector. The only thing you have to remember, which parameters is which. I mean, the order in the vector is of course important. Yeah, so you have to remember that the first element of this the first parameter's first element is sigma, or it's a second one, or so. So the order is really important. But besides that, it's pretty easy. So we can put it, and this is the definition of the Lorentz function. It's simply a definition. And if you want to solve a Lorentz equation, you have to provide those parameters. How to provide those parameters? Well, it's pretty easy. I mean, pretty easy means it's nothing changing here. So you've got initial problem, it's a vector, because we've got three equations. You've got three, if a vector consisting of three elements. You've got the time span, and it's shorter than before. It's not to 100, but anymore but to 1. And you've got parameters. And those are the same parameters as before, but you can change them. I mean, you can change them. And this definition of the problem involves the fourth parameter, and this fourth parameter is a vector right now. So we can change those numbers. But the definition of the problem and the solution of the problem, okay, this is fast because I used the time span from 0 to 1, so it will be fast. Remember that changing those parameters means something. So for the Lorentz equation, you can't put any parameter you want in here. For some parameters, it would be easy to solve the system of ordinary differential equations, but for some parameters, it would be really hard or even impossible. For some parameters, solution could not exist. Yeah, so you have to remember that you can't put simply parameters like, okay, I will put 1,000 in here. Yeah, okay, I can use 1,000. This would be easy, but sometimes you've got some minus, then it could be much harder to solve. One more thing is that this is in fact not a nice version. So I use this Lorentz with a parameter, but I've got also a nicer version of it. What does it mean, nicer version of it? Remember the first day of this workshop, you were announced that, oh, you can put any symbol, mathematical symbol in here. So we can use it. Why? Because usually if you provide somebody like this and you want to name it like Lorentz, then it will be hard to get it that this is this standard equation, yeah, the Lorentz equation, because the Lorentz equation, this is in here. Lorentz. So let me system. Where was the Lorentz? Oh, here. This is the standard the standard system of equations that are called Lorentz equations, and people are used to those parameters. That is sigma, not like p or and then the brackets in 1, yeah, or rho or beta. And so you can use, so in Julia you can use them. And it will be nicer. I mean, so I will use this nicer version. Yeah, the nicer version. From the computational point of view, I mean, computational point of view, and solving it, it doesn't matter. But for people, it will be much nicer if you will be defining the problem with the parameter, and those parameters will be get the same names or appearance as people are used to see usually. So the nicer version of it. It is like nicer. Oh, here. The nicer. We're almost done. So the nicer version of it, it's if you put the parameters like here. There are plenty of ways of doing that. You can't put more than one parameters in here. It must be a vector. So it must be a vector. But in here, you can say, okay, this is the solution. I mean, this is the function u. But I know that it consists of 3 components, but I will name them x, y, and z. This is how you use it on the paper. You can use it in Julia as well. So I am saying, okay, there are 3 components, so decompose this u into x, y, and z. And do exactly the same thing with the parameter. So I know that this is parameter, but this is the vector of parameters. So split this vector of parameters into 3 parameters that are meaningful, not meaningful, but well, the names of them like sigma, rho, and beta, and you can name them like this. Of course, you can do exactly the same with du, but usually people are like, I using like this one. So seeing this, most of people that know something about ordinary differential equations will recognize that this is the Lorentz equation. Without it, it will be hard to see. Yeah. So this is why this nicer version is not faster. It's not like you will get different result or different solution. It's somehow better. It is better for human, not for computer, not for Julia. It's better for human. It's clearer for the audiences to receive it. So if I use this this function, it's in line 1, and I use the parameters as before, but with different function, I will get instantly the solution of the problem. This is the solution of the problem. And of course, this is the solution of the problem, and in here you can solve it. And I want to show you one more. So till now, I provided you with the solution like t and u, so only that. But there are more behind it. So the solution is the whole object, and there is some information about which method was used, is it good or not, what is the return code. So if I use this solution and, okay, it's done, then you can see that this object consists of few elements. So what we know already element u, and this is the solution, in fact. So 3 equations, 3 columns, each column is responsible for 1 equation. We know that there is a time, again 28 element vector, this is a time. But what you are interested in with more complicated examples, it's like the return code. So okay, you will receive something, but is it a success or not? Or maybe it solves something. I mean, for example, the maximum number of iterations were reached, and maybe you should continue because this is not the accuracy that you are interested in. And one more thing is this one. So what was used to get this solution? And this equation was recognized as 4th order free interpolation or the stiffness aware interpolation. there are some parameters of it. So because we didn't provide any algorithm for that, so it must, Julia must recognize, so this package of Julia must recognize which of those equation is it and which algorithm you should use for that. If you provide something for that, maybe I will do that. So if you provide an algorithm, so let's copy one of the algorithms from here. We use some algorithms. Let me find it. Oh, like this one. So if you use this algorithm, well, I'm not sure it's the proper one, of course, but you can use it. Maybe let's call it solve new. It's a different method, okay? It's a different method, and you can be provided with a different solution, of course. Okay, this one is, maybe I should use a stupid one, maybe to show it. Maybe a midpoint. Yeah, which one was what were I using before? A midpoint. I'm not sure it will work for this system, but let's try it. Yeah, it's a mathematical issue, not Julia issue. Let's try, because I want to get something. Oh yeah, right now I received something else. So first of all, this obviously the solution, because it's equally spaced. So instead of 28 element vector, I've received 1,000 of elements in the vector. But this interpolation, it's different than before. So it's the third order used for this one. So what is the discretization? So you can see what was used during, and what's most important, that it succeeded to get you the result. Yeah. So this succeeded means it's really important. Yeah. You want this return code to know. You want to know if you should treat it as a solution or not. And remember, with those greater tasks, like many system of linear equations, many variables, or time span could be much longer. Yeah. So for example, if you use the time span in here, if you use the time span not from 0 to 1, but from 1 to 1,000, to 1,000. This is the definition of the problem, and you want to solve it. So if you want to solve it, you can, but probably, yeah, as you can see how many elements you have to use. Yeah. And by the way, I won't use animation for that. So you have to use not every second, every third, but not even every 1,000th step, yeah, for that. So remember that changing the time span could be not obvious for this specific method, yeah. All right, so questions, because we just about to finish, and this is the whole material. Those are all the ordinary differential equations. Yeah, I mean, if you want partial differential equations, you should use different library, or if you want to use your own discretization, it's also possible. So we can provide those for those solvers, for those algorithms, your own algorithm or your own discretization, the matrix discretization, not only automatic one. Yeah. And if you've got any questions, you can also write to me an email or contact me any other way. And if I know the result, I'll give the answer or a hint behind it. And also there are plenty of examples in the documentation for this package and different packages. It's well documented. I mean, it's pretty well documented. And of course, if you start to work with this, use the problems that you know the result. You can compare it. We can compare with the exact result or already computed result. And after that, you should move to the problems that we don't know what is the solution. Yeah. Okay. Okay. So, and on the chat there are no questions. All right. So we meet in half an hour. And distributed computing. So remember to plug in your laptops because it could involve some computations and multiprocessing. And remember that this is something that is different. So different in the case that the computer will be working, and you will hear that it will be working. Yeah, if you put a lot of pressure on it. Yeah, but yeah, multiprocessor or for the GPU or something, you can use your own. Well, it depends, of course, on what type of laptop you've got. But I assume that you've got a modern one if you use Julia on this kind of computations. Okay, so see you in half an hour.